Hi everyone and welcome to more Wet Rock and Chocolate Milk. This is the Pet Peeve series where we talk about scuba science in way too much detail. This series is for all y'all people out there with a scientific background who, like me, are a bit annoyed by the oversimplifications used in the dive industry and who are not afraid of scuba science in gory detail. Today, we'll break down water density and pressure at depth and see when it actually matters to look Mother Nature a little deeper under the hood. So, where's all this coming from? Well, one of the biggest controversies that we see in the dive industry is whether we should use metric or imperial to do our calculations. And usually the argument boils down to, well, metric is easier to calculate, and metric is the international standard. While the proponents of the imperial systems are often following some form of argument along the lines of, well, but the US. And so usually this is a very easy answer to be had. It doesn't matter, choose the metric or imperial system, whatever units you feel most comfortable in, whatever you like to calculate with, it'll be fine. However, when it comes to water density and pressure at depth, proponents of the imperial system also come up with one more answer, and that is that imperial is a little bit more accurate. So in this video, we'll be looking at that claim in a little bit more detail and see whether this is a substantiated claim. Well, first and foremost, let's review what is being taught in terms of pressure at depth. And in the imperial system, the usual statements are that we have 1 atmosphere of pressure for every 33 feet of seawater, or we have 1 atmosphere for every 34 feet of fresh water. And this is where the accuracy claim really comes from. In the imperial system, people actually do specify whether we're diving in salt or fresh water, and therefore the claim is that there is a little bit more accuracy in making that distinction, whereas the metric system basically just says take 1 bar for every 10 meters. Now, the common argument that you will find here is therefore that the metric system is somewhere in the middle between the two numbers, and therefore it's not as accurate. But if we look at this a little bit deeper, then the first thing that we want to do is we want to calculate the 33 feet and 34 feet into meters to, well, check. And what we see is that actually 33 feet is 10.0584 meters, and 34 feet is 10.3632 meters. So the metric 10 meters is not somewhere in the middle. In fact, the metric 10 meters is the smallest number of depth that will give us the 1 bar, whereas the feet seawater is about 6 centimeters deeper, and the feet freshwater is 36 centimeters deeper. So really, the question now becomes, what is most accurate for the kind of diving that we're doing? And the first thing that we need to realize here is that the metric system will give us the highest pressure at any given depth because it counts the 1 bar at 10 meters and not at 10.05 and 10.36. So this will have an impact on diving calculations. But first and foremost, we want to look at water density in a little bit more detail, and unfortunately, there are only experimental equations for water density as a function of temperature and salinity that I can find. Now, there are various versions, some of them take pressure into account, but since we're only saying, well, 1 bar for every X meters, we're going to be taking a surface approximation of water density, and we're not going to be changing that. And here the Miller and Poisson formula is accepted by UNESCO as the International 1 Atmosphere Equation of State Standard for seawater, and it is given by some basic density at 0 salinity, and then there are additional terms based on salinity that have 1 temperature curve dependent coefficient for a linear term, a temperature dependent coefficient for a, well, 3/2 power term, and a constant for the quadratic term. And here, temperature is in degrees Celsius, salinity is in parts per thousand, and density is in kilograms per liter. Now, these coefficients, just like any good formula that comes from fitting experimental data, are absolutely nasty. However, they're not that difficult to calculate. We just plug them into our favorite calculation tool, and we can actually simulate the density of water for given values of temperature and salinity. So the effective range for diving, I would argue, is a temperature between 0 and 35 degrees Celsius, or for our freedom units friends, 32 degrees Fahrenheit to 95 degrees Fahrenheit. I'd be hard pressed to think of a realistic diving condition where we are significantly above 35 Celsius or 95 Fahrenheit or below freezing point of water, although this can happen. For the salinity range, I want to argue that we would be looking at somewhere between 0 and 4.5%, or 0 and 45 parts per thousand, as freshwater is around 0%. The smaller seas, like the Baltic, Caspian, and Black Sea, are somewhere between 1 and 2% salinity, roughly speaking. The major oceans are at 3.5%, and the Red Sea, Persian Gulf, and the Mediterranean, because of evaporation, are going to be slightly higher. With the south of the Red Sea and Persian Gulf, where they're close to the Indian Ocean, we're looking at about 3.6%. The Mediterranean in the winter looks at around 3.8%. Mediterranean in the summer at about 4%, and the north of the Red Sea and Persian Gulf looking at about 4.1%. So I guess 4.5% is a good upper limit to look at in terms of what we could be realistically diving in. And with these ranges set, we can calculate the density of water for the entire temperature range and the entire salinity range. And what we find is that the lowest density, which happens to be at the highest temperature and 0 salinity, is at about 0.995, or a little below that, 0.994 and change kilograms per liter, whereas the highest density at 0 degrees Celsius and about 4.5% salinity would be at just over 1.035 kilograms per liter. Now, of course, this isn't going to tell us very much, so we can change this plot, and rather than plotting density in kilograms per liter, we can calculate the depth at which we reach 1 bar, which, if we remember, in the metric system was set to 10 meters. In feet seawater, we use 10.0584 meters, and in feet freshwater, we would be using 10.3632 meters. Now, in this plot, what do we see? Well, at the lowest density point, we're looking at about 10.2548, which is fairly close to the feet freshwater, but definitely lower than the feet freshwater value. And at the highest density point, we are looking at about 9.8376 meters, which is a little bit shallower than the 10 meters given for the metric system. And therefore, depending on where in this plot we are, it will make sense to use one over the other of these three options. And therefore, let us look at what the best value to use is. And that is in the high salinity ranges where the water is the densest, we should be using the metric system as the best approximation. Then we have a band in the middle where feet seawater gives us the best approximation, and here at the bottom at the high temperatures, low salinity level, the feet freshwater will give us the best approximation to our depth value. And this is actually a very interesting plot in my opinion. What this means is that if we're thinking about the major oceans, they are at about 3.5% salinity. So on this line, we are firmly within the metric system being the best approximation to the actual water density region. So if we're looking for accuracy of calculation, then diving in the ocean, no matter the temperature, we should be looking at using the metric system. If we're going into the middle range, i.e., diving in the Baltic or the Caspian or the Black Sea, then feet seawater tend to be the best approximation. And if we're thinking about freshwater diving, then feet seawater is still a better approximation up to about 20 degrees Celsius. So for reasonably cold water freshwater diving, feet seawater is still a better approximation than the feet freshwater value, which only becomes the best approximation at about, well, 19-20 degrees, going upwards. So realistically, feet freshwater only becomes an interesting approximation if we're talking about very warm freshwater dives. But what's that impact on diving? Well, because the metric system gives us the 1 bar pressure at the lowest depth, the metric conversion of depth to pressure is going to be the most conservative, i.e., whenever I have a given depth, the pressure I calculate with the metric system is going to be the highest of the three units used. And therefore, if I'm using this in order to calculate my gas usage and gas consumption at depth, using the metric system gives me the most conservative values. It is, as we also noted already, the best approximation for ocean diving at all temperatures that I consider realistic for scuba diving. If we're talking about feet seawater, well, it is less conservative than the metric system, and the metric system is the best approximation for ocean diving, but realistically, we're only giving about 0.5% less conservatism, which practically, I would argue, does not matter. Our gas calculations should have more conservatism than 0.5%, roughly. So using feet seawater versus the metric system, I would argue, is not really important. So the choice here is really between, do I like to do my calculations in metric, or am I more used to the imperial system and want to use feet seawater instead? The feet seawater value is also a very good approximation across the entire diving range, so there is a good argument to be using it as the default, especially if the imperial system is something you're used to. Looking at feet freshwater on the other side, well, that is only a best approximation for freshwater diving greater 20 degrees Celsius, which is about 68 Fahrenheit. So relatively limited in its application range, and otherwise it is 3.6% less conservative than the metric system, or about 3% less conservative than the feet seawater estimation if we're looking at something like gas calculations, and therefore I would argue that using that value is more likely to make us underestimate the real pressure at depth, which, while I still would argue that 3.6% should be well within our margins, is still something that goes somewhat against good planning habits, where we would like to add more conservatism rather than less conservatism. And of course, we should also keep in mind that the actual value of feet freshwater was never reached in the entire range that I would consider the normal diving range. On the other hand, if we think about our dive computers, well, the decompression calculations are purely based on pressure sensor readings and the programmed gas that we're breathing, so the computer does not actually care. If we're working in imperial units or metric, it never does the depth calculation for decompression calculations. So what it will do is it will put you at a given pressure based on the pressure sensor it has. It'll compute partial pressures based on what you told it you're breathing, and that is how it does its calculations. And if you're doing your safety stops, your decompression stops, it will still keep those relevant pressures as a part of the calculation that it's using. So for decompression calculations, setting it to seawater, setting it to freshwater, or changing the salinity really doesn't matter. What it does affect is the displayed depth while you're diving. So if you're diving and your computer is set to metric, then if it were to use exactly the 10 meters per bar, it would show you the deepest depth numbers using the metric system. Using feet seawater, if you're setting your computer to imperial and seawater values, should be slightly shallower than the metric system numbers would give you. And if you were to tell it you're diving in freshwater, then it's about 3.5% shallower than the metric values, but even that is only about 1.4 meters at a depth of 40 meters. So realistically, we're talking about 5-foot difference in the entire recreational diving range. So, what have we learned? Well, gas planning is best done using the metric system. That is the most conservative way that we can go about it, although using feet seawater is perfectly fine and it's a good all-rounder. Feet freshwater, on the other hand, is really only the best approximation for very warm freshwater dives, and even then it is less conservative than the actual density of the water that you're diving in. So my argument here is that you really want to either use the metric system or feed seawater in all diving situations. That is your conservative choice based on whichever system you feel more comfortable with. Your computers at the end of the day do not care. And therefore, use metric or feed seawater. Either of them are equally fine. If you're using feed freshwater, that is a very situational choice, and I would say that this really only starts becoming interesting if you're doing work while diving, like you're doing public safety diving. But even then, I would argue that using the actual salinity values and temperature values to get better accurate readings is better than just a generic feed freshwater calculation. Well, I hope you learned something. Hope you found that interesting, and have a good time until next time.